You brought back fond memories of the presentation at Amazon, where I think we had engineers who were comparing apples and oranges. They were comparing threads with processes, and I think it's something which we'll come back to in this talk as well. So I'm the founder and technical director of Erlang Solutions, and for those who don't know me, I've been working with the Erlang for the last 25 years when it was still a programming language. And I think from my point of view, I've seen the privilege of it. I've seen the privilege of this programming language evolve into what is today an ecosystem of languages. I think there are probably 30, 35 languages running on the beam. And I'm here today because I think my claim to fame is having worked on the first release of OTP, which, alongside Erlang has provided Jonas with the inspiration needed, to go in and create Akka. Verónica?
Yeah, hi, I'm Verónica López. I'm very happy to be here. So I'm a software engineer, currently working at DigitalOcean on the systems team, working on virtualization stuff like servers and all that, like very, very close to what we're talking about today. And also in my spare time, I'm a release manager associate on the Kubernetes team, like you would say, like the core team, although we are a lot of people there working. And yeah, it has brought me a lot of insight for this talk. And like the reason why Francesco and I decided to create this talk together was because we had a lot of very similar ideas, everyone like with their own style, of course, but getting to know Kubernetes from the really core, like the version that not everybody has given me a very wide perspective in terms of like where are we right now? So I'm very excited to be here.
So I think when I gave a talk on I gave the keynote at ElixirConf in Latin America, and I had another presenter sitting in the front row. So the keynote I gave was about how in technology we take 2 steps forward and 1 step back. And Verónica was in the front row, just absolutely furiously nodding at me, so positively, in a positive way. And her talk, had a very, very similar message to me. And as a result, I think we decided, to pair up and give this talk together. And it's always, great to work with like-minded people. And when we're giving this talk, please keep it in mind that, from my perspective, I'm giving it from a point of view of someone who's been working with the Erlang ecosystem. So, if you think I'm comparing apples and oranges, feel free to say so. And also, before we do start, I wanted to thank Jonas and Alexa for inviting us. I think it's, I think a hard time for a lot of people. I think in London, we're under lockdown right now. And the thing is, the pandemic might stop us from seeing each other in real life, but it's not keeping us apart. And I think these virtual conferences are playing a very, very important part in making this happen. So so thank you both for inviting us. So
yeah, definitely, I'm very happy to be here. Thank you for having me.
Yeah. So I think if we look at it, Erlang has had an excellent track record of predicting the future. And it was designed for the internet age, although it predates the web, and it was also designed for multi-core computers, although it predates them too. And what happened at the computer science laboratory at Ericsson is that they set out, it got invented, I think, with an intent to develop the next generation of telecom systems. So they were trying to find the tools needed to develop the next generation of telecom systems. And back in the 80s, I think, when work on Erlang got started, the only systems which had to be distributed, scalable, fault tolerant were telecom systems. And so the computer science lab came up with something truly unique. How do we program this next generation of systems? And they didn't set out to invent a programming language. A programming language just happened to be the solution to the problem. And they were successful because the problem they set out to solve was a problem of reliability and scalability of telecom networks. And ever since, when the internet came along, the problems with which you had in telecom networks back then, which had to be massively scalable. You were connecting millions of people together. You had huge spikes. They were complex, but also they could never fail. Have kind of filtered down to a wide variety of systems, everything from IoT to finance, fintech, online gaming. I mean, anything connected to the internet, I think, maps within this domain. And I think if we look at the scalability, the whole secret sauce, I'd say, to Erlang was its no shared memory approach to concurrency, which in terms make things such as implementing distributed applications a very trivial task. Once you've solved the whole problem of distribution, you automatically get scalability, you get reliability, and add multi-core architectures, multi-core processors, you automatically get parallelism. And I think these were, the very lessons Jonas took on board when he started creating Akka, back in the early days. But before we jump in, let's backtrack. Probably I'd say a good 20 years. I was at the computer science laboratory, so my very first job, and I was doing an internship with Erlang co-inventors, more or less at the same time when Java came out. And one of my colleagues at the lab came in and gave me a copy of the Java white paper. The year was 1995. In fact, it's a few months earlier. In fact, Ericsson had visited Sun Microsystems, trying to get them to pitch Erlang as a language to run on top of Solaris and Sun OS. And they were all kind of they were invited, all welcome. They'd flown all of the way from Sweden to meet them. And in pretty much halfway through a meeting, a little piece of paper started going around all of the managers in the room. And very abruptly, they went in, they cut short the meeting. And, and they basically showed an Erlang co-inventor and the head of a team who was working with it to the door. And it was lunchtime, they didn't even invite them to stay for lunch. Funny enough, this was in Facebook's current headquarters. And this was 1995, and indeed, a few months later, Java got announced. So obviously, they realized that there were a lot of similarities, because when I went in and started reading the white paper myself, I had a sense of déjà vu. There was a virtual machine. There were user threads, so there were lightweight processes. There was a concurrency model. It was different to Erlang's concurrency model, but it was still a concurrency model. There was built-in memory management and a garbage collector. And keep in mind, 1995, this was at a time when everyone was calling us, who were working with Erlang, absolutely crazy for wanting to implement soft real-time systems on top of a virtual machine. They were stuck in their ways, and they just believed that this extra layer which the virtual machine created was too slow. The only way you could implement scalable programs was in C. And the fact is, let me change slide. So the fact is that what the people who were telling us to program in C were not seeing were the real costs. And these costs were the cost of loss of productivity gains and ease of development and reduced maintenance costs, especially when it came to resilience. When you're running your program on a virtual machine, you're reusing C code. And C code was written, was used when writing the VM itself, and I wish I'd come up with that explanation back then, that at the time, Erlang was nothing other than the domain-specific language written in C. And despite us being called the crazy ones, there were three major projects we were running at Ericsson. We were doing all of the packet-based switching, all of the broadband solutions, and mobile internet. So, it was ATM switches, ATM being one of the predecessors, I'd say, to IP. which was at the time being widely used, broadband solutions, ADSL, over ADSL, HFC, so running broadband over coaxial cables, the predecessor of Wi-Fi, and even your fiber optics to the home. The year was 1997 right here. So we're actually streaming Top Gun through an ADSL network in 1997. And mobile internet, so GPRS, the predecessor to what is today 4G and 5G. And I think we learned some very, very valuable lessons from these projects. And they were that you don't have to be the fastest. You just have to be fast enough, and when speed is of importance, you use the right, when speed is of importance, you obviously go in and use C. But what was important at that point was not speed of execution, because we were fast enough. It was what was important was time to market. This was a time when you had the whole deregulation of the telecom markets, breakup of in the US into the baby bells. And those who released the product first, would get the market shares, and this, was very, very critical back then. With all of the monopolies be broken up, so all of a sudden, time to market, became just as important as speed of development and speed of the system itself, and. If you go back then, if we go in and start, sorry, let me just, So if you go back then, the JVM was a fine piece of engineering. Today, I think it's an excellent fine piece of engineering. But back then, at least we from the Erlang space, saw Java as a product, from the marketing department, which was riding the wave of the Microsoft antitrust wars. And we kept on hearing, what we kept on hearing back then was, in the next release of Java, in the next release of Java. We were just at the time moving to the Beam. The Beam, for those of you who are not familiar with the Erlang ecosystem, is the most commonly used Erlang virtual machine out there. And there are lots, I think, of talks which compare the JVM to the Beam, and we're not here to talk about that today. But I think one of the major differences, which I did not realize at the time, but which actually started dawning on me when I was at Amazon, is the whole notion of threads versus concurrency. It's the whole notion of shared memory versus no shared memory, the whole notion of mutable state versus immutable state. And we realized, that at the time, the Beam and the JVM were built to solve very different problems. In our view, the JVM was built for speed. It was built for parallelism, whereas, the Beam was built for scalability and reliability. So rephrasing this, one could say that the Beam was built for concurrency and the JVM for parallelism. So, I'll give you some examples, but what's key here is concurrency. Once you have concurrency, based on no shared state, you have distribution abstracting away from where things are executed. You could have a process running in London, where I'm speaking to you from right now, and one in Mexico City, where Verónica is from. And with the whole no shared memory approach, you do not need to worry about thread safety. You do not need to worry about mutexes, to access shared memory, or issues about network connectivity. These all became non-issues. I think, if you look at shared memory, where do you put your shared memory? How do you access it? And, what happens when you crash, when you're running in the critical section? And I think, Jonas, in many of his talks, often speaks about bulkheads and compartmentalizing. And this actually, compartmentalizing actually starts with processes themselves, and processes themselves not sharing data. So now, as soon as you've got process running in London and one running in Mexico, you've got distribution. And what distribution does is it will actually slow down the computation as a result of network latency. It will add time to your computation, but what it will do is it will slow down one single computation. If you're doing multiple computations in parallel, you will actually speed it up. And it's the same concept which we're applying to distribution as to scaling your systems on multiple architectures. So your communication across cores is expensive, but your gains are in the parallelization of your program itself. So, as I see it, the future of programming, whether we like it or not, is distributed. You need to think of your mobile app, connecting to your serverless backend. And here, all serverless means is that basically someone else is managing your servers, someone else is managing your hardware and infrastructure. Scratch under the surface, it's still a distributed system, but not only is it distributed, you'll also find most likely that it is concurrent. So this is a newspaper cutting from Contact. Contact was Ericsson's internal newspaper, which it sent to all its employees and customers. And this is an issue from 1998, where they go in and announce the first open source product. So 1998 was the day, was the year the term open source was actually coined. And also, the year the open source initiative was founded. And the first product Ericsson ever released as open source was something called Anywhere. It was basically, it was clusterware, which dynamically allowed you to scale up and scale down web servers on existing infrastructure. So, imagine, I'm half Swedish, for those of you who don't know, and imagine in Sweden, at the time, back in the 90s, my first job at Ericsson, we had very expensive Sun Microsystem workstations running, Sun OS and Solaris on our desktops. And we used them 8 hours a day, Monday through Friday. At around 5 p.m., we logged off, went home. And 5 p.m. Swedish time is more or less when the States start waking up. So, with Anywhere, what that allowed you to do was, through a distributed file server and Erlang virtual machines, running infrastructure. When we went home for the day, the computing capacity of our desktop machines could be used to run other services, such as web servers for US-based users, or email servers and others. And what these Erlang virtual machines did, was allow this load, to be spread across machines whose capacity was not being used. And the fact that they were virtual machines meant that it did not matter if these desktop computers were running Solaris, Linux, or Windows NT for that matter. They would just, you would just spin off these processes, these VMs, and they would then go in and take the load. And I think this orchestration and optimal use of computing capacity is it's a predecessor to cloud computing. Cloud computing came about 10 years later, and with it came something which we often refer to as virtualization. As always, let me remind you, if you do have any questions, please ask them on Discord, and they'll relay them on to us, and we'll answer them as we go along. So if we look at us from the Erlang community, virtualization is something we've never really come to terms with. Whilst it certainly has some use cases, throughput has definitely never been one of them. Beam is a virtual machine in itself, which is an operating system on top of the operating system. It's an operating system which schedules processes. The hypervisor simulates the operating system. The hypervisor, in turn, will run an operating system. And what I've always, struggled to explain, to the fans of virtualization, is that the more layers you go in and start adding to your system, the slower it will go, the slower it will run, and the more memory it will use. And for us, at least, where we always went in and strived to get the maximum throughput from our machines, adding layers always felt weird. We had cutting edge technology which scaled both vertically as well as horizontally. Why did we need to add more layers, consume more energy and resources, and by default you're going to require more hardware? And I think there are some really good proof of concepts with a virtual machine called the Ling VM. You can Google it, Ling VM, which runs on Zen hypervisors directly on the bare metal. So this was a this is basically an example of paravirtualization. Paravirtualized Erlang, and much like a modern container, it runs without any need of the hypervisor or any of the hardware virtualization. The Ling VM just took milliseconds to spin up, automating and setting up and tearing down of the network connection based on software, software traffic analysis. And it was all being orchestrated in a very decentralized fashion. And this was not the future. This was the whole flow forwarding project from 2015, which was at the time sponsored by Infoblox and led by its founder, Stu Bailey. And again, you can fly flow forwarding on GitHub. And it's something which, again, was way ahead of its time. So flow forwarding is very much about horizontal scalability. But if we go back to vertical scalability, in January 2012, WhatsApp, had you heard of WhatsApp in 2012? Probably not, but back in 2012, WhatsApp, when they were still in the very early days, published a blog post announcing that they'd managed to achieve a total of 2 million TCP/IP connections on a single instance of the Beam, so the prevalent Erlang virtual machine. And for a company with a very small backend engineering team, that was a huge achievement that would have allowed them to cut back both on hardware costs. Remember, at the time, WhatsApp was free for the first year, after which it cost $1 a month. And it also allowed them to cut back on hardware and operational costs. So they achieved 2 million TCP/IP connections because they were on a quest to reduce support and maintenance and overhead costs. And they did it by making changes both to the Beam and the operating system, which we were running on at the time, which was FreeBSD. Now, fast forward 3 years, in 2015, the changes which WhatsApp had been working on had been integrated into the Beam, and the changes they'd done to FreeBSD had also become standard in most mainstream operating systems. So Phoenix, which for those of you who've not heard of it, it's the successor to Ruby on Rails. It's written in a programming language called Elixir, which also runs on the Beam VM. They also managed to achieve 2 million TCP/IP connections, but unlike WhatsApp, they managed to achieve these connections out of the box on Amazon. So, this is the level of scalability, which is great, which we've always aspired for. And in most cases, it's enough, to handle probably 95% of all the use cases I personally deal with on a day-to-day basis. And for those cases where you need more than 2 million TCP/IP connections on a single machine, well, that's when you start thinking about horizontal scalability. And when I hear this, I always think back about flow forwarding. You could spin up thousands of containers in seconds. It took milliseconds to spin up an instance of paravirtualized Erlang on the Ling VM. You could tear down and orchestrate these containers as needed. And I see it very much as a predecessor to Kubernetes. It was something which, again, was way ahead of its time. And whilst it was happening at the same time as Phoenix, to actually go in and start using this mindset of spinning up and tearing down VMs, you needed to address it with a very different programming model and mindset. And again, I think you'll go in and see in GitHub, the project is no longer being maintained back then because the world in 2015 was not ready to build and at scale and out of the box. We spoke about it, but we just didn't have enough knowledge out there on how it could be done. So Veronica, over
Yeah,
to you.
so thank you. So with all of this context in mind, if we fast forward to a few years ago, another hype wave we had to live through was a containerization. I always have trouble pronouncing that word. The idea of that, that you can orchestrate these containers, well, not wrong in itself and tightly coupled to the Beam mindset of let it crash. But did it take us a step back? And it was interesting when back when I started working with Kubernetes, not at the same extent that I'm working on right now, but as a user, and most importantly with Docker and all of these distribution technologies. And my favorite programming language is Elixir and the Beam. So when I started looking at all of these technologies, they sound and look very familiar to me, and I was like, oh my god, this is just the same. Are we reinventing the wheel in a more rudimentary way? So Kubernetes is a supervisor. Kubernetes restarts containers. It also sends messages to Docker instructing it to start, pause, and stop containers. Have you seen it all before? So this is what I'm talking about, right? Like in another sense, it's like another deja vu. We already have an operating system on top of the operating system with the Beam. And so do we really need containers? And this is actually like a very common question that I get at every conference or at every meetup, or I don't know, when people know what I do and how much I like the Beam world. And they always think that they're mutually exclusive. But yeah, so I hopefully with this talk you will after this talk you will be able to know a little bit of the difference of the use cases and stuff. And but most importantly, this is since this is not like a very technical talk in terms of like a demo and stuff like that, we're talking more about the philosophy and like when to make decisions. Yeah. So the real positive thing Kubernetes and containers have contributed to is the movement towards cloud native. Cloud native is the way we have been doing things, not being bound to a particular operating system back in the days, or cloud provider most recently. Next slide, please. Yeah, I think you're muted, Francesco.
Indeed, I am. Thanks. So, there's this talk called The Future of Programming, and where is the future taking us? My view is that, with cloud native applications, the developer is abstracting away from the complexity of orchestration, from the underlying hardware and network layers. And what it does, it will let the programmer focus on, the business logic, believing they're coded their application for a single machine following a specific programming model. And the code, thanks to, I think, a lot of their underlying infrastructure, will scale, be resilient, without them having to code a single line of code. And and I think this is also very much in line with what Jonas Bonner was saying in his opening keynote when he was giving us a definition of cloud native. I think we all have kind of different nuances, and we see it slightly differently depending on what our backgrounds are and the problems we solve on a day-to-day basis. But the general overall ideas are there. And I know, from my end, I was writing my second book, Designing for Scalability and Reliability with Erlang OTP. And I felt a lot of frustration over the fact that, I was describing, how do we do scalable programs? How do we write reliable programs? And I was frustrated that I think a lot of this underlying infrastructure and a lot of these ideas are just not available today. Yeah.
Yeah. So the reason why I'm here today and why Francesca and I agree is because since most of my current work happens in the Go and cloud native ecosystem and not the Beam, I can see a similar deja vu effect that Francesca mentioned, but now with Go versus the Beam. And now especially with cloud native tooling versus the Beam. Like take in mind this word, like the tooling of the cloud native, because that is very bloated and a very strong motivation for us to put this talk together. So from a personal perspective, while Elixir is my favorite programming language, most of my current work happens in the cloud native ecosystem where I'm lucky enough to be part of important conversations humbly with stakeholders before the thing goes out, you know, that the product goes into production or is announced or launched or whatever. So I actually see the wheel being reinvented. Well, it is being reinvented. So sometimes it's on purpose, but most of the time, because it's just because people are not aware that similar tooling already existed. And I want to be clear about this point because, like, since we have given this different versions of this talk before, sometimes people tell me that I'm assuming that people that the creators of these tools are, let's say, ignorant or totally unaware, and that is not the case. Sometimes they do know, but they part of their innovation process or what they think and that from their perspective is their innovation process is not the technologies itself, but how they are presented. And I think that that brings a lot of value, but it's also another thing to keep in mind, right? So, okay. So let's say that sometimes it's on purpose for the very reason that I just mentioned, but sometimes it is not. And it's okay because even if we're very good at our whatever we're doing, doesn't mean that we have to be familiar with every single tool out there, right? So I find it interesting that among cloud native ecosystem developers, the powerful capabilities of the Beam are not well known, often not well known, or sometimes they're not even aware. Therefore, currently, developers end up setting all their expectations on Kubernetes. I don't know if you're familiar with this, like all like the strategy for fault tolerance or resilience or even availability is sent to Kubernetes. So that is a bit dangerous. Instead of giving that responsibility to the lower layers or the layers where it really makes sense for that matter. As I've mentioned in other talks, and Jose Valim has a great blog post about, when people ask me whether it makes sense to use Kubernetes if you're using the Beam, the answer comes down to the layers. Where is your problem at? The OSI model for distributed computing that you're seeing in the slides right now happens to be very handy for this. So it all comes down to that. Like, where is your problem at in these layers? And that is your answer, whether you should be using just the Beam, just Kubernetes, or both. So following up with the question of whether it makes sense or not, or even wondering if a language like Erlang or Elixir would still be relevant today, because this is like the same question, but the other side of the coin. Yeah? Given that tools like Kubernetes can now take care of it, people are usually like wary of how they can best spend their time learning new tools. So I created this, yeah, next slide, please. I created this little chart, if you can call it like that, where you can see things in common and then things that Kubernetes do one way and the Beam does another way. So for example, the fault tolerance, number one. Kubernetes automatically restarts containers that fail, while the Beam restarts parts of the application. How they supplement each other is that if we have a failure on the application level that makes it or parts of it unresponsive to health checks, for example, Kubernetes will act, saving the whole thing immediately. So that is pretty cool on the Kubernetes side. That is not something that you would expect the Beam to do because it was not designed for that. But so that's like a cool interaction way. On the other hand, having control of fault tolerance from a language level makes it easier to make more granular decisions to define a failure policy that doesn't require like to restart the whole thing or to save the whole thing. So you decide. The second thing is the service discovery. Kubernetes does this natively by automatically listing and managing the connections of the existing node. Think of nodes, if you're not familiar with Kubernetes, nodes are, for like, without losing generality, are any instance of your system. Okay, so the connection of the existing nodes is managed by this, and additionally, cloud native tools like service meshes, dedicated infrastructure layer built right into the app. Sorry. There already are some tools for the Beam languages. For example, libcluster that provides a mechanism for automatically forming clusters of Erlang nodes, just like very similar to what Kubernetes does. And it provides a publish and subscribe mechanism for cluster events so that you can easily be notified when cluster members join or leave. And a very cool project that cool and famous project that uses this is Participant. So they already take advantage of this. And the third one is live code changes. That this is also something that is, from my perspective, of course, something that a lot of people get attracted to from the Beam perspective. So both ecosystems support it, but Kubernetes does it with rolling updates, meaning that the updates happen in small subsets, and the entire set is completed only after all of them are completed in a safe way. And the Beam supports it with hot swap. So it's a totally different approach, and you literally can pick any approach that you like. So I hope that with this little chart, you get a little bit more of an idea of where it makes sense to use every tool. So next slide. But whatever you want to do or you decide to do, I always say that the way I like to frame it is with this popular phrase that says, every tool's a hammer if you want it to be, which means that any tool can become whatever you want, or like usually to highlight very creative people, the people that are problem solvers. But I'd say that in this case, we can use that creativity for something and somewhere else. So now I'm speaking of Kubernetes, but for the purposes of this talk, I'm also referring to the current modern tooling of the cloud native ecosystem. And I said in the previous slide that we should take this into consideration. Next slide, please. Because I think that this is just my very personal opinion, but again, based in my deep work on both and distributed systems in general and the cloud native ecosystem tooling and Kubernetes itself. So in my opinion, Kubernetes was released a bit ahead of its time, not in terms of innovation or that we were not ready for such a cool tool, but I think that people started using it in production environments when it was still very hard to install. And some key features are still a work in progress. There are many external tools to choose from that only cause more noise and decision fatigue at its best, and very bloated and unnecessarily complex system at its worst. Because we have so many tools out there that first I'm not criticizing. I can totally empathize with developers, new or veteran, that trying to decide where to start or what tools to pick for their entire system. And it could be very overwhelming because the current catalog is huge. So Kubernetes is often used as a quick fix for leaky software. And again, remember, it's not just Kubernetes and the cloud native tool. Or it ends up being used as the only fault tolerance strategy. When with fault tolerance, I'm saying like that, but also their only availability strategy, their only distributing strategy, and that can be a lot for a tool that is pretty cool in its concept. And I think that at some point it will be ready, but it's not ready yet. So take that into consideration.
So yeah, and this really winds me up, and I'm sure it winds Jonas up just as badly. Looking at using Kubernetes as the only fault tolerance strategy. I think we've been both of us have been saying things very differently for a long time. You need to think fault tolerance needs to be handled in all of the layers of the application. Starting with your sequential code on a process level, in a supervision tree, on a virtual machine level, on a container level, and on the hardware level. And just because you're using Kubernetes doesn't mean it's not your responsibility anymore. Developers should focus on fault tolerance in the business logic. Architect on the supervision trees, DevOps and orchestration, and VM restart strategies, and cloud providers on the hardware and network resilience. And repeating the words Jonas said today, and just because he spoke before me, doesn't mean he said it first. But I think we furiously agree on it. it's that, fault tolerance is not something you can go in and bolt on as an afterthought. You need to think about it from day one. And whilst all the examples and rants I'm giving here all focus on fault tolerance, they will apply to scalability just as well. You need to go in and manage scalability in all layers of the stack. And I think we know very well that scalability is not something which you can bolt on as an afterthought. And just to add, I was listening to Jonas's keynote earlier today, and realized that we'd gone in and actually used the same exact same tweet from Kelsey Hightower, which I think just goes to show that great minds think alike, and that we're actually all of in this together, all out to solve the same problem. So yeah, I'll give you a second to just read this tweet. So, for me, personally, this whole idea, which Kelsey is talking about, started a long, long time ago. I was actually visiting a company in the Bay Area, and I went in and I got a demo of their setup. It was, they were using Docker Compose, allowing their containerized Elixir and Phoenix-based system, to dynamically scale. They were using a Docker at the time. No one should have been using Docker, and and they were using Docker Compose at a time, and no one should be using Docker Compose. And I'm personally from a telecom background, system never failing. I went in and asked them about their monitoring, and they proudly pulled out the shiny iPhones and showed me an app demonstrating metrics. And I saw a graph stable at around 50, and I thought, okay, those were the transactions per second. Until I started looking at the app a little bit more closely, and I realized that they had the letters TPM next to it. So they had put together all of this unstable, over-engineered infrastructure to run a virtual machine, which the year was 2015, could handle 2 million TCP/IP connections, whilst handling 50 transactions per minute. And I think this is what made me realize that you want to abstract not only the programming model, but you actually want to go in and abstract the whole. You want to go in and abstract the whole infrastructure, when certain aspects of serverless, and that's when certain aspects of serverless, for me, began to start making sense. And the fact that all serverless means is that someone else is taking care of your hardware. And my view and the future and where we're heading is that now that they're taking care of your hardware, let them also take care of your scalability and your reliability.
Yeah, so with all of this in mind, the hope, not just Francesco and myself, but talking to many other interesting people in this space, is that the hope is that in a few years, no one will be talking about Kubernetes and its tooling itself. We'll be instead discussing something built on top of it. We don't know what that is yet, but will hopefully make sense for everyone and make our lives, our software professionals, easier. Nowadays, the goal was, and I guess that still is, to abstract the weight infrastructure. But unfortunately, unwillingly, and I'm saying this that unwillingly, we suddenly converted every application developer into an infrastructure engineer. Like suddenly, you have your DevOps team or your SRE team or your in-house Kubernetes expert, and instead of making, and I say this with love and like myself being on both sides of the table, instead of making everyone's lives easier in terms of like, oh yeah, I will containerize this and just deploy it. No, like a very common pitfall that I see in teams is that suddenly application developers, web developers, mobile developers, I don't know, other type of developers are required to become like, let's say, quote unquote, Docker experts overnight. Yeah? And spending a lot of time on that and not spending that time on their actual work. Yeah, so that is obviously not ideal. So yeah, hopefully in the future, all of this won't be a problem.
So, if we backtrack to the 90s, when I was working on the OTP middleware for Erlang systems, so it's basically the same middleware which inspired Akka, we abstracted away the concurrency model out of your program by introducing workers and supervision trees. Multicore came along, and the Beam allowed us to abstract the cores in the hardware. And no matter how many cores you had on your machine, be it 1 core or 32 cores, you programmed in a very similar way using the same programming model. And I think the key word, which I want to emphasize right here, is abstraction. As Verónica is saying, in the future we'll be abstracting infrastructure. And to do so, distribution and scalability have to be added to the programming models in a way the programmer, does not see they're implementing a current system running on multi-core computers in a potentially distributed environment. And I think we're heading in that direction with serverless, with stateful lambdas, and other frameworks based on the concept of reactive, event-driven, and even actor-based programming. I think cloud state is a perfect example of that. But in my view, we've just started that journey, and no doubt that for every 2 steps forward, even here, we'll be taking a step backwards. And what we need to do is, we need to go in and provide a model which existing programmers find familiar, which does not go in and reinvent the wheel, and which does not result in vendor lock-in. And again, the key to achieving this, in our view, is to use abstraction layers we've mentioned. And which we've mentioned, and uses abstraction layers to get in and not only hide complexity, but also enhance reusability.
Yeah, this will result, hopefully, in software being cloud native, vendor independent, and clearly defined layers which can be swapped. The reason we are where we are today is that we do not have this clear boundaries these days, of course, if you have been paying attention to this talk so far. So different layers are bound together, providing solutions that solve a very particular problem, but cannot be reproduced or scalable, which is goes totally against the philosophy of just plug and play cloud native software.
And when I was writing, designing for scalability with Erlang OTP, for O'Reilly, I was describing how to architect Erlang systems, ensuring that they would be both scalable and resilient at the same time. So, describe and going in and describing how you got them to scale vertically was fairly easy. We talked about all the optimizations, but when it came to horizontal scalability, I was really frustrated that there were no features which would give us all of this out of the box. I think, it took me, these were the last 4 chapters of the book, ended up being about 160 pages. And I realized, there were a lot of patterns, but almost no reusable libraries, which would be generic across, I think, a lot of these patterns. And that's when I realized that all of these layers often overlap with each other. They often go in and overlap with each other. And we had libraries and frameworks which solved a very particular use case, but they were not general purpose. An example I often give, especially as there were mentions from Amazon, was the React key value store database. It was based on, its distribution layer was based on the Dynamo principle, and which was implemented in React core. And the only data you could run would be eventually consistent data on a fully meshed, distributed Erlang cluster. So that in turn meant that if you were to write on top of it, the business logic, to run on the same node had to also be written using Erlang. And unless you went in and used the database APIs, which would then have taken you up on the application layer and possibly slowed down your system because of I/O. And it was, so what we were seeing right here was basically a programming language, mixed together with the topology, which bound you to a single VM, and all in one, in a great database. It was one of the very first kind of distributed key value stores out there, incredibly scalable, incredibly powerful, but tied in to one single use case. Again, because all of these layers all kind of meshed into each other.
Yeah. And well, so as I have been saying a little bit, this is my cherry on top of the cake. We have a similar problem on this side. There is so much tooling trying to solve very specific problems that it isn't a distinction between like the subset of tooling, the subset of the tooling of the APIs required by different audiences, like infrastructure engineers, SREs, app devs, etc. And sometimes the responsibilities are blurred. And as I was saying, this doesn't foster productivity, of course. And unfortunately, this is just the tip of the iceberg, because after all of that, you can, if you unveil all of that, you can see tons of tech debt, tons of developers, even like non-tech problems, like developers feeling frustrated with what they're doing because they are not doing the job that they were hired for, and I don't know, many little things that isolated might not be a huge problem on their own, but altogether are definitely not a good combination for productivity.
And I think this is just the tip of the iceberg. And indeed, yes, the tip of the iceberg is the only thing a developer needs to see. Today applications are completely bloated; they're almost monoliths. And think of the future. In the future, when you do a client-server call, it will be synchronous or asynchronous. Location where the callback will be executed will become completely opaque. So start thinking in terms of cloud, fog, and edge computing, as will be the replication of the state across computers. And I think it's our view that if we go in and we start standardizing the APIs between these layers we discussed in our model, including APIs for programming models, stateful, stateless lambdas, event-driven programming, reactive, publish, subscribe, or even actor-based programming, the future systems, would just be implemented on top of these APIs. So even, your typical create, read, update, delete would allow us to move all of the functionality, currently bloating our systems, into reusable libraries. Think of an extended OTP or an ACA, which today abstracts the concurrency to handle vertical scalability and resilience, but also takes care into consideration distribution, hiding the challenges of distributed programming from the developer itself. And I think look at a lot of the libraries which are coming out of Reactive, the Reactive manifesto, and the whole movement around reactive programming. And I think you'll be recognizing a lot of what we're seeing. And it will not, and what it will do is it will allow these models to come distributed to handle horizontal scale, no single point of failure, completely out of the box. So, think about just having to write the callbacks for WhatsApp, but use use the pub sub and presence APIs in the underlying layers for all of the message routing and delivery, and not having to worry about scale and resilience. So, you can, from writing everything which will run on your single machine, automatically scale to handle the 2 billion daily active subscribers which they have on a day-to-day basis. And it's the underlying layers which eventually get replaced and fixed. And the beauty of it is that you can do that without having to touch or rewrite any of your business logic. So it will allow Kubernetes and containers to do their magic, but it will not expose them to the developer. So think cloud state, but not bound to a particular programming language, ecosystem, or a virtual machine. So, I think, your take-home lesson is, ensuring you do not come up with something which will take us back a step when moving forward. And you'll do that by thinking about these layers. Divide your software accordingly when architecting it, and release these layers as open source, and make sure that they're reusable, interchangeable, and not tied into any specific use case.
In my experience, I've learned that as software professionals, and regardless of our backgrounds, it is always worth it to stop and take a look at history, see what is available, learn from the past mistakes, but also from the things that are really working nowadays. Like not only like trying to reinvent the wheel and try to come up with a very cool solution for something. Like, no, like take the time to evaluate the current things that other people already nailed. And if it ain't broke, don't fix it. Just enhance it and extend it if that makes sense. And well, I hope that that you could grab like the main pieces of what our brains have been dealing with for the past few years, and put together like here for this talk. And yeah, thank you for being here and letting us share our philosophy.
And I have to say, I mean, Jonas, Victor, they often go in and actually, Roland, when he was used to work at Lightman, often credited the Erlang world for a lot of the inspiration and ideas. But, the Erlang world actually goes in and credits a lot of the work which has been done in the reactive space on helping us starting to think and become distributed and started, getting us to start thinking in terms of horizontal scalability. So, a big thank you. Not only to you as listeners, but to everyone who's actually actively involved in reactive programming. So we're done. We will be joining the kind of speaker track. So you're very welcome to join us there if you've got any questions and ask us in person.